So you all should have seen the homework that was revealed yesterday. Is that true?
Yeah.
Good. Start here. So I will have a study guide to you by tomorrow for next Friday's exam. And then we have this homework due on Wednesday, and I will also say, let's try to get the homework 3 redo. Heck, let's call that something like next Friday. So after the exam, focus should probably be on the exam between now and then. The homework will help you with that, but I am a little bit open to pushing that back if people need the extra time. Last time we were talking about how to enumerate the couple new classes of languages that we just talked about. We just started talking about, so recursive and recursively enumerable languages. Recursive was a class of language that we can answer both yes and no to. So we talked about constructing an enumeration procedure. It involved generating 2 Turing machines, a membership Turing machine, and a generation Turing machine. We have the generator generating all possible strings that could be in the language that are based on the input alphabet. So the generator will just go through producing new strings and then pass those strings on to the membership. It writes that onto the tape. That tape is then fed into the membership Turing machine, and the Turing machine membership will spit out whether that string is in the language or not. And by this process, we can continue to enumerate and find more and more new strings that are in the language. It was a lot harder for recursively enumerable languages. We now have to think about, okay, well, we can't say no. We may be able to say no, but it also may put us into an infinite loop if the answer is no. So we want to be able to accept every string in a recursively enumerable language. Some rejected strings can cause an infinite loop, so we need some kind of diagonalization. This is very similar to what we had talked about when we talked about enumerating all of the rational numbers. So we have 2 dimensions. We have the current move, and we have a list of strings that are generated by the alphabet. Both of these are infinite or potentially infinite. So we use a diagonalization to simulate a particular move on a particular string. And some of these will terminate after some finite number of moves, and some of them will not. But that is okay, because we will, given any particular string, we will eventually start that string. And if it terminates, then we will eventually reach that termination. I just want to get a sense of approximately how clear that idea is. Do people understand the intuition behind why that is true? Maybe if you're online, PM me a number out of 10. And those who are in class, give me a thumb. How do you feel about that? Does that make sense? Okay. Let's try to make this a little bit clearer. So let's say, what would be a good example of this? Well, we saw one that was the membership problem for context-free languages. If something is not a member of a context-free language. Do we want to go with that? Probably not. Maybe I'll construct something that's a little bit more general. So let's say we have this situation where W sub 1 is a string that is in the language and terminates in 10 moves. W sub 2 is not in the language and this spins forever. W sub 3 is not in the language and we can determine this in 4 moves. And W sub 4 is in the language, and we can determine this in 17,206 moves. So you can see that there are a ton of possibilities for how this works. The question that I would have for you now is, after how many moves total would we know this acceptance or this rejection? If we wanted to do this. So what we're going to do is we have our generator Turing machine. We can still use that. So this is the TM generator. That's going to be generating these strings. And this continues forever. We just don't have a TM membership for this, because when we pass the TM membership W sub 2, it's never going to terminate. So we're just going to continue down this column forever. So we can't just go down the column because we would never terminate, we'd never get to W sub 3. So we need to have some kind of diagonalization, and we're going to do it kind of diagonal by diagonal. We're going to start here, then here, then here. I missed that already. Then here, then here, and we're going to continue to go through and simulate a single move on one of these strings. But this is the order we're going to do that in. So the idea here is that this process, this column, stops after 10 rows. After 10 moves, we terminate and can determine that W sub 1 is in the language. This will never terminate, so no matter how far we go, we will always need to continue simulating, because I'm saying this isn't in the language, but we don't actually know that until this terminates. Well, we wouldn't know that it is in the language until it terminates. We don't know that it's not in the language if it spins forever. So after how many total moves will we know that W sub 1 is accepted as a member of this language? Let's assume that this is a worst case. We don't know this initially. What is the worst case for assuming we have to do all of these moves and we don't get to start ignoring them? How many would that be? So we do the first move. We do the first move as the first thing we do. What move is the second move on W sub 1?
You can go and check 37
Yeah, in order to get here, we would have done 1, 2, 3 total moves on some number of strings. So that's what I'm trying to get at. We'd have 3 total moves to calculate the second move on W sub 1. For the third one, how many? B6. What's the progression here?
You take the moves or whatever and add them together.
Yeah, so this is 1 plus 2, this is
Yeah.
1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, 1 plus 2 plus 3 plus 4 plus 5, and that creates a ceiling for how many moves it would take. Like, for instance, this is going to terminate after 4 moves, so we don't really need to consider that too much longer. But the worst case to get to 10 positions here would be this comes up over and over and over in computer science. And I think I've mentioned that in this class, but I mention it in every class I teach because this comes up everywhere. The shorthand, 10 times 11 over 2 is 55. And this is a quadratic progression. We know this is a quadratic progression. I can't think of a better word than progression right now, but it's a quadratic function in terms of the move number. So this gives us kind of an upper bound. After 55 total generations and feeding and doing individual moves on the membership, you just do a single move and then reset. Rather than doing move on the same string, you're going to set up one string, partially computed, and then you're going to do the next move and then reset. So there'd be 55 total moves to get to the acceptance of W sub 1, assuming it's going to accept in 10 steps. 55 total moves on some string. Does that part make sense? So now the question I have for you is how many moves until we figure out what W2? The W2 is not in the language. We'll never get there. This eventually enters an infinite loop. And every time we come back to doing something on W sub 2, we will set up where we were last time and we will simulate the next move. The next move may restart a loop that's just going to continue going forever. It may be the next step in a loop that's going to go forever. The idea is that's kind of wasted effort, but we don't know that yet. There's no way for us to know that W sub 2 is never going to reach termination. So we still have to look at the next move on W sub 2 because it might terminate and accept. So we have to consider it. So we will keep coming back to it. How long will it take for W sub 3 to reject? We say that it's going to take four moves. So we know that from a recursively enumerable language, it may enter an infinite loop to reject, but we may also be able to reject. So some strings will actually be able to say no to, but some strings we will not ever be able to say no to. So if we're able to say no in 4 moves of W sub 3, what are the total number of moves that we would need to make to be able to say that? Now we're going to say this is W3 move. How many total moves by the time we do the first move?
B6.
We would do
Or no.
1, 2, 3, 4. It's the 4th move. It's a gross 4, there we go. It's a bit better. How about the second move on it?
8.
You get to here, 1, 2, 3, 4, 5, 6, 7, 8. How about the third move?
Twelve.
We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.
Okay. Yeah, it's 75.
Do we see a pattern starting to emerge? Can we abstract this idea into some kind of pattern? What would the next number be? Without even looking at the board, what would the next number be? How did I know? I didn't calculate it either. What is the length of each successive diagonal?
+1.
Plus one. So what is the position of the current one in the next diagonal? So if this was the first position in this diagonal, the next one is going to be the second position in the next diagonal. The next one's going to be the third position in the next diagonal. So if we see this is +4, this is +5, then this is naturally going to be +6. Because of that pattern that is emerging from thinking about this, abstracting it from counting it to what is the pattern that is present in that diagonal. So from there, we can start to think about, all right, what is happening? We know we're doing 3 moves before we even get started. So I'm just going to start subtracting 3 from everything. So these 3 moves that happened before this, we're going to pretend for a moment like those don't happen, and we're going to start with W sub 3. So we end up with 1, 5, 8, 11, not 8, sorry, subtracting 5, 14. So we still have, this is wrong, very wrong. 3 minus 3, and subtract 10 minus 3, 16, 4, 5, 6. But now maybe this looks like a pattern that is a little bit more familiar.
Couldn't come, not out of my head, but
So by the time we reach this 4, we would terminate. We would be at 19 total, or we would have seen 16 moves. So as long as we can generate that pattern, we can turn it into a function, and then we can plug in the associated value into that function and compute it. So I would say that when it's 4, it's almost easier to write at the table. But as soon as we have 17,206, that's going to be much easier to write out as a function rather than compute. So this is all an aside, but I think it's a worthwhile aside for just general problem solving to be able to, because this will be useful in a lot of programming problems that you tackle, being able to break it down into the associated math, come up with a general idea, and then turn it into a formula that you can just plug in. So let's actually take the time to go through it. So let's now look at W sub 4. The question we want to answer now is how many total moves have elapsed by the time we get in this diagonalization to row 17,206. Again, we're going to do this as a ceiling because as soon as this terminates, we don't need to consider that. But if we're going to worst case it, we're going to say all of these strings go to at least 17,206. How would we do that? Go ahead and take a few minutes. Try to write out the solution. How many total moves will it take to accept this string at row 17,206? Meanwhile, I'm going to go grab the eraser and I'm going to get started doing it myself.
We take 17. I don't know where it was at, 106. Can't speak. Okay.
Okay. Have an
Gonna take
answer?
17K steps before we get the result right.
So that, yeah, the answer is gonna be, according to this diagonalization,
Or I guess, yeah.
Yeah.
Moves.
how many total moves across all strings? Assuming that there are at least 17,206 strings in this language. Would it take to reach row 17,206
Alright, yeah.
following this idea?
Okay.
4W sub 4. So we can write this out as a linear expression. Since there are 6 moves before, we can start to see how this increases. So first of all, what order is this? If we wanted to try to come up with an expression of best fit to this, granted, we could just go to a regression fitter, come up with some number of rows of this table, and input that into the regression fitter that says what expression fits this. But let's see if we can do that ourselves. The first thing is to identify the order. Is this a linear expression? No. Is it a quadratic expression? We get our hint from the table. We know that 1 plus 2 plus 3 plus 4 plus something, we're starting in the middle of that, but the progression for that is going to be the same. Since 1 plus 2 plus 3 up to n is quadratic, this expression should also be quadratic. So we need to identify 3 terms. We have some x squared term, some x term, and some constant term. Luckily, here's the constant term. We identified it and pulled it out from the beginning. It won't necessarily be 6, but it'll be something relevant to 6. Maybe +1, maybe -1, something very close to it. So I'm going to work based off of this to see, can I generate some x squared plus x that gets us from 1 to 1, from 2 to 6, from 3 to 12. How would we do something like that? So we have one guess online. my intuition from that is that that is too low. I have not calculated this before, so I do not 100% know. But my gut tells me the answer is higher than that. So this is 1 squared plus 0. This is 2 squared plus 2. This is 3 squared plus 3. This isn't looking so good. We want this to be equivalent to that. So far, this is nice. This 2 matches that 2. This 3 matches that 3, which is nice. The next one, though, for move 4, this is also 4 squared plus 3. You want this to be 1, 2, 3, 4. This is going to work out for us nicely. So how do we modify things to end up with a progression that works nicely for us? My computer scientist runs screaming from math. The faster you can get this kind of intuition, the more useful it will be in problem solving, especially if you do anything like a programming competition.
And I think you could be really good and then stop doing that.
Yeah, right. I was the same boat in undergrad. It took really coming back to it in graduate school to come back to any intuition for how to set up any kind of problem like this. How do we want to proceed? Let's think about it this way. Let's see if I can draw this out in a way that's going to make intuitive sense. So one thing to do would be to draw it on a graph, and I would agree that a graph is going to be nice to kind of visualize how this is progressing. But what is something we know about everything between each of these? There's going to be at least 5 in between all of these, so we can factor that out as well.
Might have something.
So this is always growing by at least 5. And then there's another growth term at the end of it. That says this is growing by 5 plus 0, this is growing by 5 plus 1, this is growing by 5 plus 2, which is this minus 1. How do we turn that into a function? If we wanted to get the total moves here, we could do this 1 plus this constant 5 that we've talked about. This is where this 6 is going to end up. And then we add another 1 to this. This is going to be this plus 5, getting us to 7. It's going to tell us this difference, that we have 5 left. So this is plus 1 plus 2 plus 2. We get to 5 from here. Now we end up with, we need 10, which is going to be plus 1 plus 2 plus 3 plus 4. We get this constant 5. So a difference of 15. Now I have the plus 1 plus 2 plus 3 plus 4 plus 5. So there's a couple base cases here that I've gotten. This is the one thing that is wrong. There's a quick fix to this that will make all of this slide into place. We've probably spent too long on this. I kind of want to get back to the, I love the asides. But does someone want to quickly plug it into a regression calculator and see what the actual function is, just to make sure that my intuition matches with. The last thing I'd want to do is accidentally lead you astray. So anyone with a computer, go to a quadratic regression on this table. As long as it spits out an R squared of 1, we're good. How long has it been since people have done that? Have we ever taken the stats classes that have you do regressions on tables? No, it's worth demoing. Total aside of a class. We'll do very little that's actually useful here for something that would eventually be on an exam, but I feel like that is. So 1 was 7, 2 was 12, 3 was 18, 4 was. I calculated it, but that is 25. it was gonna be fun to get there.
I don't think I get that.
So let's. So those of you who have used Desmos for absolutely anything else, you can use it for regression of anything. You just enter a table. You start by creating the table, you eventually put it in the table, and you can go through the actual math. Take a stats course if you want to know exactly how to go from this to that. All you care about is that this R squared value is 1. That tells us that there's no difference between this expression that was generated and any of these points. If it hits all 4 of those points, then there's no way that it won't hit every other point in this expression as it continues. Do we agree that 7 is 0.5 times 1 squared plus 3.5 times 1 plus 3? So 3.5, 4, 7. To get to 12, 2 squared is 4, half of that is 2, plus 2 times 3.5. 2 plus 7 is 9, plus 3 is 12. To get the 18, 3 squared is 9, half of that is 4.5. 3.5 times 3 is 10.5. So 4.5 and 10.5. 15 plus 3 is 18. So this will continue to be accurate for the entirety of this expression. So now all we have to do is plug 17,206 in for x. Who wants to do that for me real quick? Could launch the calculator on my computer or my phone, but I find it to be more fun if someone does it for me. Yes. Because we're squaring something that is over 10,000. So 1,000 times 1,000 is 1,000,000. 10,000 times 10,000 is going to be 100 million.
$48,083,442.
148,083,442. Perfect. Perfect. Logan posted exactly that same thing in chat, and this thinks it's a phone number. I love it. So many digits that it's a phone number. So at least does the process make sense to people of how you could, this was a total aside. Again, I feel like hopefully this was interesting and engaging and useful, but you can use outside tools as long as you know what the tools are for, how to use them. So take this, come up with an expression for it, plug in the value to the expression, get the answer. Way easier than actually counting out where exactly it would be. But by move 148,083,442, we would have the answer for whether the 4th string that we even considered was in the language if it took that long to accept it. But the idea is that is a value that exists. If we had an infinite amount of time or a machine that was arbitrarily powerful, we could reach that in a finite amount of time. And any string that either would be accepted or would halt and reject would have some constant number of moves that would need to be made by this system in order to get that acceptance or rejection. But we could calculate it. Did going through this exercise help that to be clear as to why that is, regardless of which string, W sub whatever. As long as the acceptance or rejection is in some finite number of steps, it doesn't go into an infinite loop. Then we could calculate how many total moves this generator would need to make and the membership would need to take on what was being generated to get an answer eventually via diagonalization. How do we feel about that? Does that help? Does it blow people's minds? Is it too early for this? Something like that.
I mean, I don't think I'd ever come up with that expression, but yeah.
Yeah, it was, I mean, even I was having a tough time. I was working out the -6. So I thought we'd eventually have a +6 here or something close to it, but it was fairly close to that. It just meant that we had to factor out some more of it and find that. Yeah, it was certainly challenging. It was going to be a challenge to get to that point, but we do have tools that as long as you understand what you're doing, you can go plug it into the tool. Cool. The last couple of minutes, let's at least summarize and try to get a little bit of somewhere today. I love my asides a little bit too much. All right. So there's a language class beyond that that is recursively enumerable. And that is everything that is outside of that language class. Those that are not recursively enumerable. What would it mean to not be recursively enumerable? So to be recursively enumerable, we can accept in a finite number of steps, but we don't reach any conclusion about rejection. Could spin forever.
Which means you can reject in a finite state, but never accept. Yeah,
Maybe
opposite.
to not be able to answer the acceptance question. We could have something in the language, a string in the language, and defining a machine for that would spin forever before even being able to say that that was in the language or not. So this idea is basically something that is unprovable. It's true, the language exists, but we cannot produce, even enumerate the language. So are there any examples? Can you think of anything that's not recursively enumerable? Listing all the real numbers is an example of something that is not recursively enumerable. Even all reals between two arbitrary endpoints. So we have all reals between 0 and 1. We talked about this a little bit last time, I think, but the idea is that we want all numbers, all decimals of finite length, all decimals of infinite length that repeat, and all decimals of infinite length that do not repeat. All real numbers between 0 and 1. Why can't we enumerate it? Yeah, well, we have an infinite number, but there are some infinite sets that we could enumerate, like the positive integers or the integers or the rational numbers. We have a really hard time enumerating. In fact, it's impossible to enumerate all the reals because it's actually a really fun proof. Future. Go put it out, fire department. So we can assume that we have some infinite countable set the question that I might start asking is the power set of that set countable? That's another example of something that's not recursively enumerable. I guess we're kind of out of time, so I'll come back to this at the start of the next class. But we'll start with this idea of why can't we enumerate the real numbers? Because that's a really interesting question. And it turns out to be a fun proof that you basically assume that you have a table of all of them. Assuming that we've enumerated them, that somewhere in some row of this table, there exists a query. We can show that even if this table is infinite, we can generate something that is not in the table. So we'll come back to that tomorrow morning. I have office hours starting now, if anyone would like to go over any proof types to get started on the homework. I'll see you tomorrow.